All right. Hi. On this video, I'm going to go over the answers to force body diagram 2. So here we go. A person pushes a 10-kilogram box to the left with a 20 Newton force at a constant speed. All that's really important, well, we got the constant speed. The constant speed is important because that tells us that we have balanced forces. So our downward force, we obviously have the weight force, which is going to be equal to, right, remember that weight or force of gravity is equal to m times by g. So in this case, right, it would be 10 kilograms times by, right, instead of 9.8, we can just use 10. And so that's going to give us, right, a weight force of 100 newtons. So you can use 9.8 instead of 10 if you want, just simpler to use 10. So that's going to give us 100 newtons. We also have the normal force, which is the force of the table pushing up on the table pushing up or the ground pushing up on the box. That is also going to be 100 newtons because we have to have balanced vertical forces. Someone is pushing it to the left with 20 newtons, so we should have a force to the left with 20 newtons. And then, right, since it's moving at a constant speed, we also need to have friction to the right. And that is also going to be 20 newtons. So force diagram should look like that for number 1. Number 2, a paperweight is sitting on a stack of papers. So it doesn't matter that it's sitting on a stack of papers, right? It's just what are the things that are touching it. So obviously we're going to have our weight force, and that's just going to be 0.5 times by 10. So that's going to be 5 newtons. And we're going to have, right, the papers are going to apply a normal force upwards, also equal to 5 newtons, because we have to have balanced vertical forces. So often when you're thinking about doing this, you just think about like, okay, you have gravity, and then you think about like what is touching the object. So in this case, right, the only thing that's touching it is those papers. The papers are acting as a surface and pushing upwards, applying a normal force. Next one, you have an air supply crate being dropped out of an airplane. Air resistance is negligible. So the only force, because nothing is touching it, the only possible force that we could have on it is the force of gravity. So in that case, your weight force is going to be 30 times by 10 or 300 times by 10, so 30,000 newtons. No upward force because, right, it's not sitting on a surface. No force of friction because it says air resistance is negligible. That means that we can ignore it, or that it's so small that it's unimportant or insignificant. So next one, a basketball rolls at a constant speed across the gym floor to the right. Constant speed is going to be the important part there. It means that, right, there are balanced forces horizontally. When it says that it rolls, that means that it's not being pushed. Like it kind of insinuates that it's rolling along without being pushed. So there's probably no force of friction and also no push force. So it leaves us just the vertical forces. So that gives us, we would have the weight force. 0.6 times by 10 is going to give you 6 newtons. You would also have the normal force upwards, which is also going to be equal to 6 newtons. And then again, no horizontal forces because it says it rolls across the gym at a constant speed. The rolls means that it's not being pushed. And so if it's not being pushed and it's going at a constant speed, then there's no force of friction either. A football is flying through the air to the left. Doesn't really matter what direction it's going or it's flying through, right? The only thing that can be acting on it if it's in the air is the weight force, right? Every other force has to be applied by a contact, by some sort of contact. The football is not touching anything, so therefore it can only be the force of gravity. A 5-kilogram box being pushed with a 20 Newton force to the right across a frictionless surface. So here we go. We got our weight force, obviously. So that's going to be 5 times by 10 is going to give us 50 newtons as our our weight. And then we're obviously going to have normal force also be equal to that. And then we have a 20 Newton force to the right, sorry. Okay. Now this is interesting because it's the first, this is one of the ones that's more obvious, but like in this case, right, we obviously have unbalanced forces because we have a force to the right without a force to the left. And so what that tells us is that this object would be accelerating to the right um, because it's being pushed to the right, yet there's no force resisting that. So in this case, it would speed up. There would be an acceleration to the right. I mean, number 5 and number 3 are also the same way, where there's a force down with no force upward, and so the object would accelerate downwards. And we kind of expect that, right? Because the football is falling, right? So it's obviously accelerating towards the ground at 9.8 meters per second. So then moving on to the next one, number 7, a 30 kilogram child on a skateboard is traveling to the right at a constant velocity. Constant velocity means that it's going, right, that we have balanced forces. The 4 is not important information. It doesn't matter how fast we're going. That's just trying to trick you. So we can ignore that piece of information there. We got to, right, we obviously have the weight force or the force of gravity. So that's going to be 30 times by 10, so that's 300 newtons. And then we also have the, let's see here, the normal force on the child, also 300 newtons. And there's no forces, right? It doesn't say the kid is pushing themselves, so it just kind of insinuates that they're just kind of gliding along. And so since they're not pushing each other, then there's pushing themselves, there's not a push force. And so since there's not a push force, there's also not a force of gravity, or sorry, a force of friction. Because again, it says constant velocity, so we have to have balanced forces horizontally. So if there's no force push to the right, then there's also no friction to the left. Next one, a 8 kilogram cart is being pushed to the left. So we got 2 newtons that way. Okay, it says it's frictionless, so let's see. Then we also have 8 times by 10, so weight equal to 80 newtons. And normal force is also 80 newtons. Real quick, right? So vectors that are the same or forces that are the same, we should attempt to make them similar lengths. I mean, they don't have to be like measured with a ruler or anything. Obviously, if you can make vectors that are smaller, but it's not to scale, right? Like, um, this 2 is not obviously 40 times smaller than the other ones. So just try to make it smaller, visually smaller. It doesn't have to match, right? I mean, obviously it's a deal if, um, if they are similar looking links, but vectors that should be smaller should be obviously smaller. Vectors that are the same should be visually the same. So it's just, we're not going to get a ruler out here to measure them. So. Okay, a 1.2 kilogram light fixture is suspended from the ceiling by a chain. So we obviously have the weight force, or the force of gravity is pulling down on that. So 1.2 times by 10 is going to give you 12 newtons. And then you're going to have an upward force, and that upward force is applied by the chain, which is a tension force. So that's our first one of those. Obviously, the chain is also going to have to apply a force of 12 newtons to balance out the force of gravity on that object. We have a 5 kilogram birthday present with a 3 kilogram package stacked on top of it. Okay, so this is where it's going to start getting a little bit interesting. So let's think about this. We have the birthday present, probably sitting on the table or ground or something. Then there is another 3 kilogram one stacked on top of it. So think about the forces. So obviously we have gravity. So that's going to be, right, the weight force, which is equal to 50 newtons, 5 times 10, right? Um, we also have, right, the top package is going to be pushing down on the lower package, right? So we're going to have a downward force from that package. And so that force is going to be the weight of that package. And so it's not a weight force because it's not the weight of that object, right? It's going to technically be a normal force, um, because it is the surface of that of the surface of the upper package is pushing on that. So technically, it is a normal force equal to 30 newtons, right? Again, because it is a surface. I guess present. They're called presents, huh? Not packages. Okay. So that's why it's not a weight. It's the weight has to be of the weight of that particular object. So the weight of this birthday present. So because this is a separate present, it's going to be a normal force because it is the surface of that present pushing down on it. Then you're going to have your upwards force. I don't have a ton of room here, but it's going to be equal to, right? This is also a normal force. Normal force by the this is the normal force of the floor or table or whatever, and that's going to be equal to the sum of these two, right? It's got to be balanced, so that's going to, right? If we have a 50 and a 30 downwards, we need to have an 80 upwards. So, so something like that. Ideally, that I can make that one a little bit longer, but I don't have a ton of room. So, so okay, we have a 3 kilogram book on a table and a 4 kilogram book is stacked on top of it, and a 2.5 kilogram Navi climbs on top of that. So, right, we kind of got this book, which is 3 kilograms. Then we have another book, 4 kilograms, and then we have a kitty cat. Oh, I was doing so well up until the ears. Okay, I don't know. There you go. That's all you get. Um, so we can treat the package and the cat as though they're one thing. So, right, you can kind of think about these two things being as though they're one. We have a 4 kilogram book and as though there's 6.5 kilograms, right? Because the 4 kilogram book and the 2.5 kilogram cat, right? You can just think of them as a, you know, 6.5 kilogram object sitting on top of it. So that makes it just like number 10, because, right, the cat, you don't need to do a separate force for the cat because the cat isn't actually touching the book. You can just treat it as though it's one 6.5 kilogram book. So going back, so we have the weight of the book, which is just going to be 3 times by 10, so that's going to be 30 newtons. We have the weight of the, right, just like before, except this time it's 6.5, so that's going to be the normal force of that upper book, which is going to be 6.5 times 10, so 65 newtons. And then we'll have the normal force from the floor or table, which is going to be the sum of those two things. So that normal force is going to equal 95, right? 30 plus 65. Again, ideally, I would have made that longer, but I ran out of room. But, if this is 30, this should be twice as much, and this should be equal to kind of those two things added together. Let's see here. suppose I could do that kind of, do this. That's a bit better, isn't it? Okay, we have a 6.5 kilogram book on a table is being pushed by a hand with a 5 Newton force, but is not moving. So we have our weight force or our force of gravity. So that's 2.5 times by 10, so that's 25 newtons. We also have the normal force, which is going to be the same, being pushed by a hand with a 5 Newton force, but is not moving. So it doesn't say the direction, so I'm just going to go ahead and assume that it is to the right. So and if it's not moving, there needs to be some friction force here. To balance that out. Okay, on to page 2. A 6.2 kilogram shopping cart is rolling on the ground at 14 meters per second. 14 is not important. What is important is that it is moving at a constant speed. The 14 meters per second kind of tells you that it's moving at a constant speed, like a constant 14 meters per second. So in that case, you have again the weight of the shopping cart, which is 62 newtons. We would also have the force of the normal force, should also be 62 newtons. And then it says it's rolling. So rolling kind of means not pushed. So if it's not pushed, then there's no force to the right or to the left, to the right. And if there's no force to the right, then there can't be a force to the left slowing it down because it's moving at a constant speed. So I need balance forces horizontally. And so if there's no force to the right, then there's also no force to the left. So a ball is moving to the right at 4 meters per second through the air after being thrown. Well, if it's in the air, the only force that could possibly be acting on it, as long as there's no air resistance, which is generally assumed, would be the weight force, or the force of gravity, which would just be 7 newtons. That's all. The 2.5 kilogram brick is sitting on a 14 kilogram table. It doesn't matter the weight of the table because the table is not above the brick. So in that case, you would just have your weight is equal to 25, and your normal force is also equal to 25. We have a 2.5 kilogram Navi is sitting on a 0.125 kilogram piece of paper, which is sitting on a 45 kilogram desk. Same thing, both of these objects are below Navi, so it doesn't really matter. You just have weight of Navi and then the normal force, right? Basically, this normal force is being applied by the paper as opposed to being applied by the desk or table in number 15. So 15 and 16 are basically the same problem, just the normal force in number 15 is being applied by the table, right? By a table. And in this case, is the normal force is being applied by the paper. So that's the only difference there. Number 17, how do we measure an object's inertia? By measuring its mass. And then our last set here is a ball is hit upwards with 300 newtons with a racket. Draw just after the ball leaves the racket. Okay, so if it's not touching the racket, then it is no longer applying the 300 Newton force. So we do not take that into account, right? Now it's just flying through the air. If it's just flying through the air, only force that's acting on it is right, the force of gravity, which is 0.4 times 110. So that's 4 newtons. That's it. No 300 newtons because it's not touching the racket anymore. You have to be touching the racket in order to have that 300 newtons applied. Okay. A wooden crate on a table is being pushed with a 25 Newton force to the right by hand, but is not moving. Okay, so let's get we got our vertical forces here. Weight is equal to 72 newtons. That means we have a normal force of 72 newtons. Then we have a force to the right of 25 newtons. And we would then have a force to the left of force of friction, right? Because it's not moving, that means we have to have balanced forces. Well, because it's not accelerating, we have to have balanced forces of friction is also equal to 25 newtons. Okay, next one, a 3 kilogram book on a 70 kilogram table. Okay, 70 kilograms doesn't matter, with a 2 kilogram package on top of it, and then Navi is on top of the package. So kind of this similar sort of situation. We have this table, it doesn't matter. Then you have a book. And then, right, so that's 3 kilograms. And then you got a package on top of that. And then you have Navi. So there you go. Again, just like last time, we are going to treat Navi and the book as though they are one thing. Right? So instead of being a 1.7 kilogram cat in a 2 kilogram package, these are a 3.7 kilogram item. Okay, just like the one up above. So what that means is, right, we have the weight force, actually, 3 times by 10 is going to give us 30 newtons. We then have the force of the package, which is technically a normal force because it's the surface of the package, and it is going to be 37 newtons. And so then we have the force of the table, which is a normal force, and it is going to be 67 because it is 30 plus 37. So that's going to be 67. And then we have this last one. 200 kilogram refrigerator is being pushed with a 50 Newton force by a person to the right, which moves at a constant speed, and it doesn't matter what the constant speed is, right? Constant speed just tells us that it's moving. It has, right, its net force is 0, meaning we have balanced forces. So we have the weight force of the refrigerator, which is 2,000 newtons. We have the normal force on the refrigerator, which is the floor, 2,000 newtons. We then have someone pushing to the right with 500 newtons. And it is moving at a constant speed, so that means we need to have friction, which is also 500 newtons to balance that out. So there you go. That's what number 21 would look like. What does it mean for a free body diagram to have balanced forces? Okay. So if it has Okay, so if a free body diagram has balance forces, that means the net force is zero, which means the acceleration is zero, which means it is moving at a constant speed. And that constant speed could be 0 meters per second, meaning it could be at rest. So, so that's what it means to have. It means your acceleration is zero. You're not changing your speed. Okay, I hope this video helped you answer some questions for you. So, hope have a good day.